Okay, welcome Bradley and Caesar and Jordan and Jesus and Ralph and who are watching this and coming soon. Let me share my desktop and I'll talk about what we're doing today. Okay, so here's the plan. I'll start out as always with questions that you might have. And then we're going to get into quadratic forms. So we'll start out with the easiest ones, which are ellipses and hyperbolae. So hopefully you still remember all about ellipses and hyperbolae. But what you may not realize is that there's a lot more ellipses and hyperbolae than you learn in pre-calculus. In fact, we're going to find out that there's a whole big collection of them you've never seen before in terms of the equations. And the reason why you may not have seen them before is you need linear algebra to really understand them as an ellipse or a hyperbola. So we'll talk about how to use linear algebra to take an ellipse or hyperbola that's not in the form you're used to and put it into the form you're used to. So one thing is you can actually know that it is an ellipse or hyperbola. So we'll talk about that. And then we'll move to high order. So again, you learned probably last quarter, maybe the quarter before. And remember you talked about quadrics, things like ellipsoids and hyperboloids. Do you remember that stuff?
Yeah, like surfaces.
So you could talk about surfaces, and that's like one level up, right? That's XYZ instead of XY. Do you think you can go a level after that?
Mathematically, yeah.
Do you think you could do it physically?
No.
Absolutely, you're doing it right now. Okay, how many of you are not going through time right now? As in, it's the same time it was, in your memory along, a while back. No, time changed. So it turns out you just don't think about it. But no, 4D is what we live in. We don't live in 3D. We live in 4D. So we're going to you can move up a level and then talk about in the X, Y, Z, T space. And you can still talk about quadratic forms. Does that make sense?
Why can we only travel in one direction along the fourth dimension, but the rest of them we can travel in 2 dimensions?
I think you need to get religious for that one.
Okay.
So the answer is every experiment we've ever had says that you can never go backwards. At least not you personally. Does that mean it can't happen? Like, 1,000 years from now when our technology is amazingly better. Think about 1,000 years ago. Maybe we'll be able to go back. Who knows? Okay. Positrons can. So there are things that do go back, but it's a little weird. And also they do all kinds of weird things. So I'm not going to get into that. But the why, nobody understands the why, why is gravity the constant that it is? It is because it is, and every experiment shows it is. And that's all you can say. Okay. So it's a fact that unless we do some really weird thing that we don't know how to do yet, or we go in the same direction in time. Don't ask me why. Okay. Anyway, so we're going to get into quadrics. Okay. And we're going to get into quadrics in however many dimensions we need to. And as you might guess, it has everything to do with matrices. Okay. And eigenvalues and eigenvectors. So that's what we'll talk about. And then I mentioned last time that I'm going to get ahead a bit. And do you remember why I'm getting ahead a little bit?
We have an exam coming up.
Yeah, there's an exam coming up on Monday. So I want you to be ready for that. So that's a big thing to note, is that there's an exam coming up on Monday. So I want to make sure that I have ample time to kind of go talk about the exam, review kind of problems that you haven't seen in a while, so that you don't get crushed on the exam. So which means that I have to get a little ahead today. We got a little ahead last time. I'll get a little more ahead today. And that way I can spend, some ample time talking about the exam on Friday. So the getting ahead is this 5, 6, and 7. And to note that the 5, 6, and 7, the homework for that will not be due until a week from today. But I want to talk about it a little now so I can do the exam. at least a piece of the exam review on Friday. Then you take the exam on Monday, and then your homework's due on Wednesday for this 5, 6, and 7 stuff, which is 9.1. So what we'll talk about is I'm going to let you guys think about it, is what are the properties of addition and subtraction of matrices? So I'm going to have you come up with that. And then once we see that, then we're going to realize that we need something to describe kind of all the important stuff all at once. Instead of having to go back every time you go into something, you have to re-describe it and reprove things and have new theorems. You want to have theorems that just work for everything you do. And that's always nice. So whether it's matrices or numbers or polynomials or exponentials or sines and cosines, you want to be able to have properties and theorems that describe it all. So that's what we're going to be doing. And that big generality, which I've kind of warned you about all quarter, is called vector space. So it's a big day today in that we're going to define what a vector space is. And that's going to allow us to talk about a general theorem and then not have to prove it every time you go into something different. So we'll have 3 main examples today. And there are a lot of examples, by the way, not just 3. One is Rn, and that you've already seen. You know what a vector is. Okay, that's what we've been spending the entire quarter on. Do you know what Pn is? You know what that means, that symbol? Anyone know?
Does it have to do with P, like from diagonalization?
Good try, but no. No. P stands for polynomials. So we're going to look at the set of all polynomials of degree n or lower. And that's what Pn will correspond to. And then hopefully you know what n by m means. What does that represent?
A matrix that is not square.
Actually, it could be square. So a matrix. Your first 2 words are better. A matrix. Because remember, n could be 5 and m could be 5, and then it's square, right? So you could either say a matrix, or you could say a matrix that's not necessarily square, but matrices. And it turns out that whether it's Rn, polynomials, or matrices, I know they don't look anything alike. It turns out they really are alike. And we'll talk about that and realize that they're all vector spaces. And then I'll give you an example, if we have time, of something that isn't a vector space. So that is the plan today. Are there any questions about homework or anything else? Any questions? You can say them, pop in the chat, whatever you want. Quiet group today.
Actually, yeah, can we go over number 6?
Okay, number 6 on 7.4, I believe. Just a minute, let me go grab it. Just a second. All right, this one, right?
Yeah, that's the one.
Okay, so let's read it. Find the eigenvalues and an orthonormal basis of eigenvectors for A. Okay, diagonalize A by finding an orthogonal matrix U and the diagonal matrix D such that U transpose AU equals D. Okay. The funny thing is they say find the eigenvalues and then they say hint the eigenvalues are -3, -2, and 1. So if you can't find the eigenvalues, it means you didn't read the question. Do you agree?
Yeah.
Because I just found them, -3, -2, and 1. Sound good so far? So don't you love easy questions? Okay, well, we just found the eigenvalues. Now we need to find eigenvectors. By the way, how do I know that there aren't going to be any two-dimensional eigenspaces?
We have 3 eigenvalues.
Exactly. We have 3 eigenvalues, and that means that the eigenspace with one-dimensional eigenspaces add up to 3, and it's a 3 by 3 matrix. That's the most you can have. Is that clear?
Yeah.
Okay, so that's just one note, is that makes it easy. That means we're not going to do Gram-Schmidt or anything like that. Is that the worst we're going to have to do is divide by magnitude. Does that make sense? Okay. Also, how do I know that this is actually a problem I can do? That there really is an orthogonal matrix U by looking at the matrix.
It's symmetric.
Exactly. It's symmetric. And we had a big theorem that said if you got a symmetric matrix with 3 eigenvalues and a 3 by 3 matrix, then it's always orthogonally diagonalizable. So that means we're in good shape. All right, so now let's go do it. Okay, I always like to, get strategies first. And the first thing I always like to do is make sure that I actually have a chance of doing it. Uh-oh, where'd it go? Just a minute. Okay, so what I need to do is I need to find the eigenvectors. How do I find the eigenvectors? What's the process? Hopefully y'all know by now. We've been doing this for a couple weeks now.
Put them into A minus I times lambda.
Exactly. We're going to go A minus lambda I. And let's just start with -3. Just do them in order. So that means we're going to subtract -3, which is add 3 along the diagonals. Any questions on that? So let's go and do that. And let me make a matrix out of it. All right. Is it okay if I do the arithmetic in my head? -5/3 plus 3 is 4/3. Any questions on that? Okay. And then the others are the same mess. I'm not gonna type the others in because I don't want to waste your time. Is that okay? -14/5 minus a -2 is -4/5. And 7/15 minus 1 is -8/15. Any questions on the diagonals that I just wrote? Okay, and the others are the same. They didn't change because we're subtracting 0 from all the others. So that's why, is it okay if I leave them blank for now? Any questions on that? Okay. A problem like this, how would I expect you to do this one?
With a computer.
Absolutely. That's why I didn't type everything in. I don't want to waste your time because it'll take forever for you to type everything in and then do RREF one at a time. And no thanks. I hope you don't want to do that either. Am I right? But I will ask you because I can't do it in my head. What do you get when you RREF? So you can put that in the chat box. Is probably the best way to do it. And while you're doing that, I'll make a matrix out of it. I know some of you must have done it. It's not that hard.
For that one, as the RREF red as rose, I got 10 square root 5.
Okay, next row.
And then 0, 1, -2 square root 6.
And then my guess is you got 0, 0, 0 for the next row. Am I right?
Yes.
You better have. Otherwise, it's not an eigenvalue. Any questions at all on RREFing and knowing how to do it in a computer? So again, you're allowed to use a computer on the exam for this kind of thing. And you're also responsible for knowing how to use a computer. So if you have any troubles with it, that's the kind of thing you can ask for help. And I'd be happy to help you out. But you are responsible for knowing how to RREF on the computer. Okay, so for this one, we want to find a null space. And usually you just start with something easy and then we'll adjust. So I'm just gonna let Z be 1. Sound good? So what I can say, let me insert symbol equation and bracket. So if Z is 1, then that means you get negative root 5. Oops. We get 2 root 6. And 1. Okay, but why is that not the vector we want? I purposely did the easy one to let you know that's not the one we want.
It's not orthonormal.
Exactly. It's not, let me use the right word. It's not a unit vector. Orthonormal is like the whole matrix. It's not part of an orthonormal matrix because it's not a unit vector. So how do you make this a unit vector?
Divide by its magnitude.
Yeah, find its magnitude and then divide. So I get 5 plus 24 is 29 plus 1 is 30. So I need to divide by the square root of 30. Any questions on that? Nobody said this was going to be beautiful. And then 1 divided by the square root of 30. Okay, and that now is a unit vector, and I'm guaranteed that it'll be orthogonal to the other two that I find by plugging in -2 and 1 into A minus lambda I. Right? Because that's what the theory tells us. Any questions on that idea? Okay, so I just found one of them. And you could think of this as the first column. Okay, this is the first column of the P matrix, right? Do you need me to go and work out the second and third columns, or do you have the idea now?
Yeah.
You have the idea? Okay. So the idea is we do exactly the same idea, work out the second column, work out the third column, and then combine them to make a matrix of 3 columns. And then what is D, by the way? That one I can do without too much typing. So let's work that one out. Because remember, to diagonalize a matrix, you need to find P and D. And P inverse. Did it happen? Let's try again. Oh, I bet it's down here.
Be -3, 2, -2, 1 across the diagonal, right? And then zeros everywhere else.
Yeah, so that's going to be, yeah, I was just having trouble getting the matrix to show up. That was my issue. So let's try again. There we go. So bracket, make it 3 by 3, because that doesn't take too long. So the idea here is we have -3 as the first one, and then the second 0, 0, 0, and then -2. and then 0, 0, 0, and then 1. And that is the D matrix, D for diagonal. Any questions on that? So again, to find the P matrix, we found the first column, you find the other two in the same way. And how do you find P inverse the easy way?
Take its transpose.
Yeah, take a transpose. And I'm hoping you can all take a transpose in your sleep, can you? Okay, that's supposed to be easy. Inverses are not easy. Transposes are easy. So the idea is that if you have an orthogonal matrix, then the inverse you can do without any issue. You just take a transpose, which is easy. And then you just write your PD and P inverse and you're done. Any questions on that? Or P inverse DP is, sorry, they want P inverse AP is what they want, equals D. Is the way the question is worded. Does that help?
Yes.
Okay, very important. You notice, I mean, all these questions, diagonalizing a matrix, we've been doing for, this is like, I think our 3rd or 4th day of this. So you do need to know how to diagonalize a matrix. And I do want to let you know, not this example, but I want to make sure that you know how to diagonalize a matrix by hand that has nice numbers. Because anyone know why it's really important that you know how to do that for your life? I mean, not for your life, but for the next 7 days.
We have an exam
We have
that
an
you might
exam.
ask us to do it.
Yeah, what do you think question 1's going to ask you to do? Yeah.
Could be diagonalizing. Yeah.
By hand, yeah. Okay, it's not going to be, and it will be nowhere near as messy as what we're looking at now, by the way. But I want you to know I want to make sure you know the process of diagonalizing by hand. Got it? And then all other examples, anytime it's messy, use a computer. Sound fair? Okay, so any other questions? Any other questions? If not, we can move on. Okay, if there's no questions, I'm going to move on. And this is very much review. Hopefully you remember this from years ago. So it doesn't look anything like linear algebra either, does it? So recall that if you have ax squared plus by squared is 1, then if a and b are both greater than 0, you have an ellipse. And I'm going to like cheat a little bit. I'm going to say that a circle is an ellipse. Are you guys okay with that?
Yeah.
Yeah, sometimes we just say it's an ellipse with eccentricity 1. And that it just makes life a lot easier because you don't have to keep saying, well, it's an ellipse unless you have 1 and 1, because that's a pain. So we're just gonna call circles ellipses, and then you don't have to worry about it. Okay, and that works pretty well because in the real world, do circles exist?
Definitely.
No, they don't actually,
I was going to say rarely.
because a circle has to be perfect and exact, right? Is there anything perfect and exact in the real world?
No.
No.
So ellipses exist. Circles really don't exist. But you can get real close to a circle. So for example, the orbit of the Earth actually is close to circular, not perfectly. Do you know that?
Yeah.
Yeah. I mean, if you saw it on a map, then you wouldn't be able to tell that it wasn't circular, but it isn't circular, by the way.
Same thing with the planet, right? It's kind of close to a sphere, but then it's elliptic. It's actually an elliptical spheroid.
Yep. Same thing with the Earth itself, not even the orbit, is it's elliptical. And even if you zoom in more, you don't even get an ellipse because there's things like where we are right now, at least where I am, Tahoe, we have a mountain. It's got little bumps and stuff, right? But it's called, a good model is an ellipse. Any questions on that? So an ellipse is when a and b are both positive. So if you have something like 3x squared plus 4y squared equals 1, do you all know that's an ellipse? You're more used to seeing it as x squared over 1/3 plus y squared over 1/4 equals 1. It's the same thing. Okay. So whether you put it whether you put it on top or bottom, it doesn't make a difference. It's still an ellipse if you have numbers in front of the x squared and y squared. Any questions on that? Okay. And if A is less than 0 and B is greater than 0, it's a hyperbola. So if you have something like negative x squared plus y squared is 1, that's a hyperbola. Now, you learned this a long time ago in high school, probably, right? Sounds right? And similarly, if A is positive and B is negative, so that'd be like x squared minus y squared equals 1, that is a hyperbola. Do you agree? Any questions on this very, very basic review? Okay. By the way, what if you had say plus 2x at the end? Does that change whether it's an ellipse or hyperbola?
No, but it changes the center, right?
Yeah, it just changes the center. So all that is a translation. Any questions on that? So for today, we're just gonna say we're gonna let our center be the center. You know what I mean? We're gonna let our origin be the center. Sound good? And if you let the origin be the center, you don't have to worry about like a plus 3x and minus 4y or something like that, because you can always make that adjustment and just redo your variables. Is that clear? That you learned in pre-calculus and intermediate algebra. Any questions on just a little review of ellipses and hyperbolas? All right. So the bigger question is, why am I talking about this? Any guesses? Right? What have we been doing all quarter? And does this look like anything like what we've been doing all quarter?
No, it's not
No.
linear.
Okay. Turns out this is exactly what we've been doing all quarter. Okay, but it doesn't feel like it, right? So here's what we're gonna do. The question is, what if you have a quadratic form ax squared plus by squared plus cxy equals 1? Okay, that one you can't just move the axes to the left or right or up or down and get rid of that cxy. Do you agree? There's no completing the square that'll work here. Any questions on that? Okay, have you ever been asked to graph something like x squared plus y squared plus 4xy equals 1? Have you ever been asked to graph that? Right? Seems reasonable, doesn't it?
Yeah.
It's not like there's even any calculus in it, right? It's just basic algebra. Have you been asked to graph this? Okay. So I will let you know personally, I learned how to do this before I learned calculus. But do you know why?
It took linear.
Because I'm weird. Hopefully you've learned that by now. I'm weird. They didn't have anyone at my high school that knew calculus, as in they didn't have any teachers. So they didn't have anyone to teach me calculus. So they gave me everything that didn't need calculus. And that included linear algebra. I actually had this course before calculus, but I had to be self-taught. So you don't need calculus to do this. But what you do need, as you might guess, is linear algebra. So it is algebra, but it's not, you may not see this and know. So here's what I'm going to have you try doing. And I want you to do this on your own. I'll give you a couple minutes. It shouldn't take more than 2 minutes. I have a matrix, and actually let's do this, equals 1, just for fun. So I have a matrix equation. So the equation is the vector xy as a horizontal vector times the matrix A, B, C, D times the vertical vector xy equals 1. And I'm going to give you about a minute or two. It shouldn't take longer than that on pencil and paper to work this out. Okay, this you could have done the very first week of class. All it is matrix multiplication. You don't need to do any fancy stuff. I'm not asking you for rank or anything like that. So give it a shot. Tell me what you get. And when you got it, put it into the chat box. And if you have questions or need help, I can help you. But hopefully this isn't hard. This is just matrix multiplication. That's all this is. Little simplification at the end. Well, first thing, there needs to be an equal sign because the equal one doesn't go away, by the way. And second is when you're done, there shouldn't be any vectors left, actually. That's a hint. So it turns out when you're finished, it's a 1-by-1 matrix, and usually you don't even write parentheses around a 1-by-1 matrix. Because notice we have a 1-by-2 times a 2-by-2 times a 2-by-1. And when you look at the dimensions, that gives you 1-by-1 when you're done. Okay. And what I want you to do though is combine like terms. So you gotta do the basic algebra. So if you have two terms that both have an xy in it, then those should be combined. So Ralph, you're really close, but you can simplify just a little bit. And x and y are numbers, they're not matrices, so you can say xy equals yx, or yx equals xy. So let's see what y'all get. It's better to not factor the x and y out. So you want to write it as something times x squared, something times y squared, something times xy, in terms of the best algebra way of writing it. But you're close. You did the linear algebra part right. Okay, maybe I'll write out the answer because hopefully you'll see that it's the same, except it's a little prettier the way I write it. So the answer is ax squared plus b y squared. Oh, sorry, plus dy squared plus b plus c xy equals 1. Any questions on how I got that? Any questions on that? So I see some of you have different stuff, but this is the right answer. Any questions when you multiply these out? This is what you get. Okay, so the main thing to realize is that we can go forwards or backwards. Now it turns out that this B and C, there are lots of choices. So if I had something like, write out the matrix 4, and now let's do 1. How about 5x squared minus 3y squared plus 7, how about 8xy equals 1. Any questions on the question? Okay, why are there different choices? So I'm going to write it, and I have this form that's going to work. And I got to decide what A, B, C, and D are. Why do I have do I have different choices for A?
No.
Nope, that one's got to be what?
5.
That's 5. Do I have different choices for D?
No, that has to be -3.
Yep, that one's -3. Any questions on that? What about B and C?
There's a few things that could add up to 8.
Not just a few, there's an infinite number of things that add up to 8, right? I could do 1,000,008 and -8, right? I know you were all thinking of that one, right? Okay. I don't want to do that one. What do you think the best thing to do is? What do you think the best choice for B and C are?
4 and 4.
4 and 4, because then I have a symmetric matrix. And whenever you have a quadratic, you can always write it as a symmetric matrix. What's good about symmetric matrices?
We can do stuff with them.
I'm looking for a big long word.
Diagonalization.
Yeah, actually 2 long words, not 1, but 2 long words. So what kind of diagonalization?
Orthogonal.
Yeah, I can orthogonally diagonalize. Okay, so if I choose B and C to be equal to each other, then I can always orthogonally diagonalize the matrix. Any questions on that? All right, now the interesting thing is, when I orthogonally diagonalize it, and I'm going to do it just kind of in symbols first. When I orthogonally diagonalize, I'm going to end up with the following. I'm going to end up with xy. That doesn't change. Oops, I got to do it this way. There we go. Times P times D times P inverse times xy. Equals 1. Any questions on that? Okay, now this is where things get interesting. If I look at the P inverse XY and I look at the XYP, I can think of this now. And in fact, I could look at the PD inverse, kind of thinking of it that way too. I can think of this as remembering when you have something like PDP inverse, then P is a change of coordinate system. It's a change of basis. Do you remember that? So we can think of P as a change of basis matrix. Any questions on that? And not only is it a change of basis matrix, but it's an orthogonal change of basis matrix. Do you remember what orthogonal matrices do to the plane? What do they do to the plane?
Nothing.
Yeah, they rotate. Okay. So what the P does is it rotates the plane and P inverse rotates it back. Is that clear? So this says we're going to start with our XY, we're going to rotate it, then we're going to do D, and then we're going to rotate it back. Any questions on that? And the interesting thing is if you have an ellipse and you rotate your ellipse, does that make it a hyperbola? What do you think?
No.
No. And if you have a hyperbola and you rotate your hyperbola, does that make an ellipse?
No.
No, it doesn't. So what this says is that the P is actually not important at all in deciding whether you have an ellipse or hyperbola. Any questions on that? What tells you whether you have an ellipse or hyperbola?
The D.
The D. It's all about the D. So you don't even need to find the P if you just want to decide whether you have an ellipse or hyperbola. All you need to do is you need to find the D. And finding the D means that you just need to look at the characteristic equation, characteristic polynomial. Any questions on that? Okay, and if you want to find out if it's an ellipse or hyperbola, what you're really doing is saying that if you look at this diagonal, do you have positives or do you have one of each? Does that make sense? Any questions on that? If you have a positive and a negative, then you have a hyperbola. If you have both positives, you have an ellipse. Okay. And D, what are the entries of D?
The eigenvalues.
The eigenvalues. So what this says is once you have taken your equation and turned it into matrix form, and once you get the use of it, do you think it's hard to turn this equation into a matrix form? Or do you think that was really easy?
Easy.
Yeah, that's easy. Okay, there's very little to do there. I hope you guys all agree. So basically, to find out whether you have an ellipse or hyperbola for this particular equation, all I have to do is look to see if the eigenvalues are positive or negative. Any questions on that? Okay. How do I find out if the eigenvalues are positive or negative?
You find them.
Yeah, you find them, and you find them by doing what?
We could use our formula since it's a 2x2.
Yeah, characteristic polynomial, and with our formula. So that says we're going to take lambda squared, and then we're going to subtract the trace. What's the trace of this example?
2.
Okay, 2 lambda. And what's the determinant of this one?
1.
Negative
So it's
31.
yeah, you gotta be real careful. 5 times negative 3 is negative 15 minus 16. So it's negative 31. We set that equal to 0. Now, I don't even need to actually find the roots. If I just want to find out, is this a hyperbola or is this an ellipse? Why do I know immediately? Just kind of by knowing just math, not linear algebra.
If you wanted to think about it as factorable, you're going to have one value that's higher in negative and one value that's positive.
Yeah, let's take a look at this. It's negative b, which is 2. Okay, plus or minus the square root of b squared minus 4ac. B squared is 4. 4ac is large. Do you agree? Right, 124. So we're looking at negative 2 plus or minus the square root of 100 and negative 2 plus or minus the square root of 120. And notice that if you take negative 2 plus or minus the square root of 120, then that you'll get one positive and one negative. Because if you add the square root of 120, that's positive. And if you subtract, that's definitely negative. So notice this has positive and negative roots. Therefore, what can I say about the shape of this 5x squared minus 3y squared plus 8xy equals 1?
It's a hyperbola.
Yeah. So therefore, the curve is a hyperbola. Any questions on that? Okay. What if you wanted to find out? I don't think I'm going to spend the time doing it, but what if you wanted to find out how much you needed to rotate that hyperbola? How would you find out how much you needed to rotate it? What would you have to find?
P and P inverse.
Yeah, actually just P, because P is a rotation matrix. So you find P, and then you remember that a rotation matrix is sine of theta. Do you remember this? So it's cosine theta, negative sine theta, cosine theta. So you just take the inverse tangent of y over x, and that'll give you your rotation angle. Any questions on that idea? So if you want to find out how much it got rotated, that's it. Okay, and just because I love astrophysics, one example where you care is that if you happen to have let's say a rogue planet and it goes into a solar system and you want to find out whether it's going to get trapped into orbit or is it going to just move a little bit and then just leave the solar system. Do you guys know about that? Have you heard that before, the different shapes? Hopefully you know if it's in orbit, what's the shape?
An ellipse.
An ellipse. Okay, and if it leaves orbit, because maybe it was going too fast, what is it?
Parabolic.
Yeah, hyperbola.
Then it's a hyperbola. So these these coefficients of the matrices are determined by the speed and the angle basically that it's going towards. Okay, and gravitational attraction. So that's an example. It's kind of fun. Is that based on the gravitational attraction and the angle, you can actually come up with, is it going to get trapped and become a planet of the solar system, or is it just going to be a rogue planet and just get out of there? Like that, we had a rogue comet that went. I don't know if you read about that a few months ago. It was kind of cool. Okay, so that's one example. It's a fun example. And there's a lot of others. I just like astrophysics. Any questions on this idea? Any questions at all on this? Okay. So Here's one example. Let me give you a more fun example, one that you're used to, that you have seen before. And you know what it is, but we're going to actually prove it. Or I'm going to have you try. All right. You've seen this curve before, right? Y equals 1 over x? You better have
Yes.
seen it. What does it look like?
That's the butterfly one, right?
Butterfly. Yeah, it's one way of describing it. But we're going to actually realize that it's something special.
Like hyperbola?
Are you sure it's a hyperbola?
No.
Let's prove it. So what I'm going to do is I'm going to multiply by x. Sound good? Y'all agree you're allowed to do that on both sides?
Yeah.
And you get xy equals 1. All right. What's the next step?
Set up a matrix.
Yeah, set up the matrix. Okay, set up the matrix equation. So I'm going to steal this one so I don't have to retype in matrices. So in this case, what are the diagonals going to be?
Zeros.
Yeah, they're zeros. There's no x squared term and there's no y squared term. So that means they're both zeros. How about the off diagonals?
1/2.
Mhm.
1/2.
All right. Now it's starting to look like we've been doing, isn't it? All right. What's the next step?
Diagonalize.
Yeah, we diagonalize it, and we do that by finding the characteristic polynomial. Okay. And if we want to just show its hyperbola, you don't actually have to do the full diagonalization. All you have to do is get the characteristic polynomial. What's the trace of this, mate? Of this one?
0.
Yeah, this is like the easiest trace in the world, right? So it's lambda squared, and it's minus 0 lambda. I can get rid of that. And then what's the determinant?
-1/4.
Mm-hmm. So that's going to be minus 1 over 4 equals 0. What's lambda?
Plus or minus 1/2.
Plus or minus 1/2. So have we proven that we have a hyperbola?
Yes.
Yeah, because we have a positive and we have a negative. If you get two positives, it's an ellipse, right? If you get one of each, it's a hyperbola. So we can say lambda equals 1/2, or let's go negative 1/2, or it's equal to 1/2. Just a note, let's just continue because this is, like I said, it's an easy example, so let's go for it. So let's diagonalize this guy. So now let's start with the negative 1/2. It's nice and beautiful. If I subtract negative 1/2 I, what do I get?
1/2.
Yeah, I get 1/2 everywhere, right? Okay. Hopefully you don't need a computer to RREF this. What do you get?
One, 1.
Yeah, you just get 1, 1, 0, 0. Okay. And that immediately tells us what we have. So, and by the way, if it's negative 1/2, things don't change much except it's going to be negative 1/2, right? So that you're going to have negative 1/2 along the diagonals. So what you're going to get, I'm going to skip to the chase because it's pretty easy, is our P matrix is going to be what? Well, if you take the first eigenvalue, notice that's going to be 1, -1, or 1 over root 2. Because we want to make it orthogonal. And -1 over root 2. And the others will just be 1 over root 2, 1 over root 2. Because basically you get 1, 1 for the other one. Any questions on that? Okay, now we can realize this as a rotation matrix. How much is it rotated by? Remember that the first one is the cosine. If the cosine is a half, what is your angle?
Pi over 6. Or pi
Oh,
over
sorry,
2.
if the cosine is 1 over root 2, not 1/2. If the cosine is 1 over root 2, what is your angle is what I meant. What's your angle?
It will be 45 degrees or pi over 4.
Pi over 4, I don't talk temperature. So this is a rotation by pi over 4. Is the way the axes are changed. Does that make sense? Isn't this pretty math? I guess beauty's in the eye of the beholder, but I think it's beautiful. Okay, and that's what you kind of knew already, is that y equals 1 over x was your butterfly. Okay, but it's a butterfly rotated. Okay, it's got a rotation. Okay, or it's got a hyperbola rotated by pi over 4. Any questions on that? So we're totally able to understand what this conic is by diagonalizing our matrix, because we know it's hyperbola. We know that it's rotated by pi over 4. Okay, so I want to move on to the next level. All right, so let's suppose you have a higher order quadratic form. Okay, now in third quarter calculus, you got things like x squared plus y squared plus z squared equals 1. In fact, x squared plus y squared plus z squared equals 1. What is that in a word?
A sphere.
That's a sphere. Okay, but on the other hand, if it was 2x squared plus y squared plus z squared equals 1, what is it?
An ellipsoid.
An ellipsoid. Okay, what if it was x squared minus y squared plus z squared equals 1?
Hyperboloid.
That's a hyperboloid, right? So you learned that last quarter, right? Now comes the fancier piece, and that, what if you have more terms? So what if you have an xy term, an xz term, and a yz term? Okay, then it's much harder to look at it and decide whether it's an ellipsoid or hyperboloid. Do you agree? Okay, it's not going to be easy at all. On the other hand, if we have ax squared plus by squared plus cz squared plus dxy plus exz plus fyz, we can actually write down this as a matrix equation. And the nice thing is it's basically what we just did, except we're going to have xyz instead of just x and y. So more typing. So if it takes a moment to get this typed out, you'll understand. So I'm going to put an x, a y, and a z.
It's going to have the equation's still going to have the same form, just one dimension greater.
Exactly. We're going to have, it's going to be a 3 by 3 matrix instead of a 2 by 2 matrix. And then it's going to be times an xyz. Okay, what are the diagonals? That's the easy part. What are the diagonals of the matrix?
ABC.
ABC. Okay. Now this D, where does that go? And the hint is think about what we just did with 2x2s. Okay,
We
it
put them
could
in the corners.
not the corners, because this corner right here is first row, third column, and that would be an XZ, not an XY. Do you see that? So we don't want them in the corners. We're going to put them here, because right here, this is the XY, first row, second column. So first row is X, second column is Y. And also here, because that's second row, first column, and that's YX. And we're going to split the D into two pieces, so I'm going to have D over 2. How about the E? Where does that go?
Third column, first row.
Yeah, that's the corners. Okay, so that's going to be the corners. And we're going to split up in two pieces, E over 2 and E over 2. And the F, that should be obvious now because there's only two places left. F over 2. Because this keeps it symmetric by splitting it in half. And then I guess finally, we have equal 1. Got to put that in there. Okay, and if you work this out, if you multiply this matrix equation out, you get what's on top. Do you believe that?
Yeah.
Yeah, it's just going to happen. All right, and the good news is nothing is different. So I don't think it's worth me doing like a full example because it's really exactly the same as what we just did, except now we have 3x3, which means a lot more numbers and a lot more typing. But pretty much same idea is if you want to find out what the shape of the surface is, then what do? 2 words.
Orthogonally diagonalize.
Yeah, we orthogonally diagonalize a matrix. And when you orthogonally diagonalize a matrix, which you know you can do because we have a symmetric matrix, then you look at your D, your diagonal matrix, and if they're all positive, then you get an ellipsoid. Whereas if you have a mix of positive and negatives, you have a hyperboloid. Any questions on that? That make total sense?
I have a quick question.
Sure.
So suppose you wanted to find out what surface you have, you do.
Mhm.
And then I wanted to find the area, the surface area. How would you go about that?
So now you want to do the calculus on it.
Yeah.
Okay, so the idea here is if you have an orthogonal matrix, then you know that the determinant is 1. Is that clear?
Yeah.
Or -1. It's either 1 or -1. Is that clear?
Yes.
Okay, so we know the determinant is 1 or -1, which means, now thinking last quarter, the matrix transformation isn't going to change the volume. Is that clear?
Yeah.
Which means you could diagonalize it, look at the equation from the diagonal matrix, and then you just have your standard form that you're used to having with just an x squared, a y squared, and a z squared, and none of this messy stuff. That's the whole point of diagonalizing, right?
Yeah.
And then you do what you learned last quarter. You triple integrate. Does that make sense?
Yeah, that's cool.
Yeah, and it works. And that's if you wanted to find out the surface area or volume, what you do is you just transform it using an orthogonal matrix, because an orthogonal matrix is a rotation. And if you imagine taking a surface, okay, or a solid and rotating it, is that going to change the surface area or is it going to change the volume?
Not at all.
Exactly. And that's why you can get away with that, is that you can multiply by the P and the P inverse and it doesn't change anything, because it doesn't change the surface area and it doesn't change the volume, because orthogonal matrices are rotation matrices. Okay. Now things get more complicated in 3D, right? With 2D, you just say if you have a rotation matrix, you just find theta, right? But hopefully Bruce showed you in 3D, it's a lot more complicated, right? To
Yeah.
understand how it got rotated, because there's a theta and there's a phi. So I think I'm not even going to go there and assume that you learned it last quarter. Sound good?
Yeah, thank you.
Okay, so the great thing is you can do this. Okay, and by the way, you can do higher dimensions too. Same idea, is you can decide what you've got. You tend to have more language as soon as you get up higher dimensions, because it's not just an ellipsoid and a hyperboloid anymore. So the language that they use, especially in physics, is the signature of the matrix. So the signature of a matrix is the number of positive eigenvalues and the number of negative eigenvalues. Okay, and that's called the signature of a matrix. Any questions on that definition? So by the way, just as an example, where we live has a 3-1 signature. You don't know why?
Are you talking about Tahoe or the Earth?
I'm talking about not just Earth, the universe, most of the universe at least. Okay. Why are there 3 and then something else is different?
Because we live in 4-dimensional space.
Right. There's time and then there is space. And time is the 1, and that actually has a negative eigenvalue, okay, in the matrix in time space. And space is x, y, z, that's 3 dimensions, and those all have positive eigenvalues. Okay. On the other hand, if you're unlucky enough and you decided to like take your spaceship and go into the nearest black hole, okay, bad idea, by the way, then it turns out your signature switches. And you get 3 negative eigenvalues and 1 positive eigenvalue in the time-space continuum. So that's why I said most of the universe, but not all of it. Inside black holes, everything switches. And I'm not going to be able to explain what's going on, but you can trust me. Sound good? Things get really weird. Okay, any questions on that? If you do, I'm not going to answer anyway, because it's too hard. But if you take a full relativity class in, upper division, not at our college, upper division, then you'll learn about this stuff. You'll learn a little bit if you take it. Is it next quarter that class is offered?
Yeah, modern's next quarter.
Modern physics is next quarter.
Yeah, so they might touch on it a little bit, but again, it's pretty intense, so they might not. I don't know.
Does anybody know if Bruce or Kathy is teaching that yet?
I was just asking. Do you know who's teaching it? You
It's
guys
both.
are the ones that apply. Signed up.
It's both. Bruce is doing lecture and Kathy's doing lab. 'Cause she's
Interesting.
okay.
unionized, and Bruce hasn't yet.
Huh? Interesting. And my guess is lecture is probably online, right?
Yes.
Eve. Yeah. And lab is probably face-to-face.
Yeah.
Yeah. So when you go to lab, she'll take you into a black hole and you get to like experiment. Just kidding. Okay. So now I have an exercise for you. So we're going to move on. We're just a note. This book has some weird quirkiness. We're moving from chapter 7 to chapter 9. We're skipping chapter 8. And the reason is you've already had chapter 8. And I actually have no idea why chapter 8 is even part of this book, because it doesn't belong. So there's a reason to skip it. So just to note, chapter 8 is spherical coordinates, cylindrical coordinates, and polar coordinates. And can I trust that you already know what those are anyway? And do you agree they're not linear algebra?
Yes.
Yeah, so I have no idea why it's in the book. So we're skipping that chapter. Sound good?
And don't you use matrices to do the conversion to one another? Like,
The Jacobians, but actually, if you read the book, there's no matrices in that chapter.
oh, that's weird.
There's no linear algebra in that chapter. So that chapter should be skipped. So I'm skipping it. So we're moving to 9.1. And I want to let you know that the homework assignment for 9.1, I'm reminding you a second time, is not due until a week from now. So I'm getting ahead of the syllabus so that I can spend a little extra time on review on Friday. And hopefully you agree that's a good idea. Do you agree? That you'd like a little review?
Yeah.
Maybe you don't want review, but most people do. Okay, so we're getting ahead a little bit, but I figure I could do that. So I'm going to jump into 9.1, and I want you to do something. And I want each of you to put in the chat box a property of the real numbers with addition, or what's not subtraction? That's a mistake. Multiplication. And let me write scalar multiplication. Okay, and scalar multiplication is multiplication, by the way, when it's just real numbers. But that also holds for matrices. So here's your task. You have to put one property in the chat box that is not already in the chat box. So if you're first, you don't have to worry about it. Yours will be the first, and it can't already be in there. Okay, and there are, let's see, 7 of you here. So I want 7 answers. And by the way, there's a lot more than 7. I'll do the rest of them. So I want you to put one property of the real numbers that is also true for matrices that either involves addition or multiplication, and scalar multiplication for matrices. I'm sorry, regular multiplication for matrices. And put it in the chat box. So let's get rid of the word scalar. Okay, good. Jordan's got one. The commutative property of addition, a plus b equals b plus a. Okay, and notice that's true whether you use capital A and B or whether you use lowercase a and b, whether you're thinking of matrices or whether you're thinking of numbers. Okay. Jordan, Jordan, you already got one, so don't do another one. You'll make it too hard for everyone else. Everyone
Yeah,
does
sorry, I jumped the gun.
So Cesar, you can say the word, but also write down the equation or the formula, because it turns out there's more than one associative property. Okay, Bradley just did the associative property for addition. Okay, Victor just did. Yeah, Jacob, you just missed it. Victor just did the distributive property, except that all of it should be lowercase k, but I'm sure that's okay. For matrix, for multiplication. There's a lot more of them. Okay, in fact, I have 10 that I'm going to show you, and there's only 7 of you, so you should all be able to get one. Some are so obvious you're not even thinking about it. Oh, good, good. Ralph just did the associative property of multiplication, which is not the same as the associative property of addition, even though it looks similar. And Cesar, you just missed it. That's why being fast is good. Good, good, good. Jesus just did the additive identity, the existence of 0, whereas a plus 0 equals 0. And if you're looking for another one, there's one similar to what Jesus just did. Good, good. Ralph just did a times 0 equals 0. Okay, and that's the and that's a property. It's one we're not going to use, though, it turns out. And similar to Jacob's, we're not going to use that one either. because the transitivity really is for non-equal stuff is what you really care. Okay, a plus a is 2a. That's true. It's actually not a property though. That one you can easily prove from the properties. I'm gonna let you struggle a little bit more and then I'll give you all of them. All right. All right, shall I show you the list? You ready? CA plus B equals CA plus CB. That was a distributive property. We got that one already. I'll have to see who did that one, but that one already happened. Yeah, Victor did that one. Okay, sometimes they're so obvious you don't think about it. Okay, let me go do them. And let me write down, there are 5 for addition, and there's 5 for multiplication. So these are the additive properties. The first one, which was so obvious, none of you even thought about it. If you take any two of them and you add, you're still in it. So if you add 2 matrices, you get a matrix, don't you? If you add 2 numbers, you get a number. Do you agree? And that's a property. It's an important property. Okay. By the way, why is the dot product not a good, can't be used for this as a new kind of a plus? What's wrong with the dot product?
Is in a different dimension.
Um,
Not a matrix, it's a number.
yeah, the thing is if you dot 2 things, you don't get a thing anymore. So if you dot 2 matrices, you don't, I mean, sorry, you dot 2 vectors, you don't get a vector. You get a number. Does that make sense? Whereas a good old fashioned addition, if you add 2 things, you always get one of those types of things. If you add 2 numbers, you get a number. If you add 2 matrices, you get a matrix. Any questions on that? Okay, number 2, you guys already said, V plus W equals W plus V. Number 3, you also said. So number 2, by the way, was the commutative property. Number 3, U plus V plus W is equal to U plus V plus W. That was the associative property. You guys got that one. Number 4, you got also, and there exists a 0 such that 0 plus V equals V for every V. Okay. And again, for matrices, that's the 0 matrix. For numbers, it's a 0 number. Any questions on that? And number 5 is for every, if you have one, whether it's a matrix or number, there always exists a negative of that thing, such that if you add it, you get 0. And that's called the additive inverse property. Any questions on properties 1 through 5 for additive properties? I want to note something, is that given properties 1 through 5, you can prove anything that you already know about, basically. Okay, anything that involves addition only. Any questions on additive properties? Okay, and then the multiplicative properties, let's write those in. And they say the following. First, if you take a scalar and you multiply, then you stay in it. So if you take a number and you multiply that number times a matrix, you're still a matrix. If you take a number and you multiply that number times a number, you're still a number. Is that clear? Okay, number 2 is a distributive property. So if you take a number times v plus w, you have AV plus AW. Okay, so if V and W are matrices, then that works. If V and W are numbers, that works. Do y'all agree? Okay, then you have the other kind of distributive property, and that is if you take the sum of two numbers times a matrix, for example, then that's the first number times a matrix plus the second number times a matrix. Any questions on that? So it turns out there's two kinds of distributive properties. Okay, the fourth one is the associative property for scalar multiplication. So a number times a matrix is you can multiply the two numbers first and then multiply by the matrix, and it works. Any questions on that? And then finally, no one thought about this one. I think this is one of the easiest of all of them. If you take the number 1 and you multiply by a matrix, you don't change the matrix. You just get that matrix again. Do y'all agree? And if you take the number 1, multiply by a number, you still get that number. Any questions on that? Okay, so there's 10 different properties. Okay, and you have learned these all your life. Do you agree? There's nothing new here. Is that clear? All right, so here's what's new. What we're going to do is we're going to say, well, what if you have something that has all of these properties? Any questions on that? So the collection of all matrices, say n by n matrices, then that has all 10 properties. The collection of all numbers, that has all 10 properties. Okay, can you think of anything else that has any other collection that has all 10 of these properties? Any thoughts?
Vectors?
Yeah, vectors. So if you take two vectors, in fact, I use V and W to make them look like vectors, then do you agree that all 10 of these work? I'll let you look through them. So if you take a vector in Rn, then that's going to have all 10 of these properties. Can you think of another thing that has all 10 of these properties? Any thoughts?
Polynomials?
Yeah, polynomials. So if you look at all polynomials, has all 10 of these properties. Do you agree? Anything else? And the answer is there's a whole lot of other examples. See if you can think of more.
I want to say functions, but I'm not entirely sure.
Okay, well, let's think about functions. Is there anything that doesn't work? If you take two functions and you add them, do you get a function?
Yes.
Okay, if you take f plus g, is that the same as g plus f?
Yeah.
If you take f plus g and then add h, is that the same as taking f plus the sum of g plus h?
Yes.
Okay, is there a zero? So a function that is the zero function, so that if you add that to a function, you get what you started with.
Most likely.
Yeah, how about f of x equals 0 for all x?
Yeah.
Do you see?
Mm-hmm.
Is there a negative? Given a function, is there a negative of that function? So if you add it, you get the 0 function.
Yeah.
Sure. Like if f of x is cosine x, then negative f of x is negative cosine x. Right? It always works. Can you take a constant, a real number like 7, and multiply that real number by the function? Do you still get a function?
Yes.
Yeah. Does it satisfy a times v plus w equals a, or a times f plus g? Is that af plus ag?
Yes.
How about what a plus b times f is that af plus bf?
Yes.
How about a times b f, is that the same as a times b f?
Yeah.
If you take a function and multiply by 1, do you get the function back?
100%. Yeah.
So we just proved that a function satisfies all 10 of these properties. Okay, so the collection of all functions satisfies all 10. Okay, there are a whole lot of things that satisfy all 10. So because there's so many things that satisfy all 10 of these, we have a name for it. And this is that big definition. So this is a really important definition for this quarter. I say that a lot, but this is one of the biggies. And that is a vector space, V, is a set of elements along with addition and multiplication operators that satisfy all of the above 10 properties. Okay, so functions, we just kind of went through each of them. That is a vector space, the set of all functions, such that addition is function addition, and then scalar multiplication is regular old scalar multiplication of functions. Any questions on that? Okay, so the next 2 weeks, this is what we're talking about. We're talking about vector spaces. Any questions on this idea? Okay, so linear algebra, believe it or not, is all about vector spaces. So let's do some examples and we'll just go through them. How about Rn? Okay, Rn, those are vectors, right? You can look at Rn as vectors or points. It doesn't matter. It's the same. Do you agree?
Yeah.
So if you have vectors in Rn, do they satisfy all 10 of these?
Yes.
Yeah, no problem. Okay. If you're worried about one, I could prove it, but they're pretty obvious. Any questions on any of these 10 properties? I do want to give you a disclaimer. This section is not on the exam. Does that mean you don't have to ever worry about it?
No.
When do you have to worry about it?
No.
Huh?
The final.
The final exam. Okay. And afterwards too. When you get into your upper division courses, you're going to be using this stuff. Just let you know that. Okay. So, don't ignore everything I say because it's not on the exam in 5 days, but you still need to know this stuff. So Rn, the set of all vectors in Rn, is definitely a vector space. Okay. To write out the full proof, do you think that'll be long or short?
I think you would need to do it 10 times.
Yeah, not 10 times, but you need to do 10 things. So what I'm going to do, because I don't want to waste your time either, I'm going to let you pick a number from 1 to 10, and I'll prove that one.
5 on multiplicative properties.
Okay, so that's 10, by the way. We're going to call that 10. Okay, so that means there exists a 1, such that 1 times v equals v. So let's prove that. So I'm going to prove one of them. If I had to prove all 10, there isn't even enough time to do all 10 in the next 15 minutes. So proof of number 5 for multiplicative properties. And by the way, it's always a good idea to write down what we're trying to prove, because if you don't know what your goal is, you'll never get there. We're trying to prove 1 times v equals v. Oops. Okay, so what does a v in Rn look like?
A vector with n components.
Yeah, so it's going to look like we have 1 times So instead of V now, let's write down what a vector is. And a vector is going to be x sub 1, comma, x sub 2, comma, dot, 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 comma, x sub n. Any questions on that? And I guess I should write 1 times V equals. Just by definition. All right, now, what does it mean to do scalar multiplication? By definition, that means I'm supposed to take the 1 inside each of them. Because isn't that what scalar multiplication is?
Yes.
So that's going to be 1 times x1, comma 1 times x2, comma dot dot dot, comma 1 times xn. That's equal to, well, what is 1 times x1? It's not a trick question, by the way.
X sub 1.
X sub 1, comma, and what's 1 times x2?
X sub 2.
X sub 2, very easy, comma, dot, 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 and 1 times x sub n is x sub n. So you'll find these proofs are very tedious, takes a long time, but nothing's hard. And by the way, that by definition is V, and we're done. Any questions of the proof of number 5 from multiplicative properties?
Yeah, as far as proofing goes, this isn't proof by example because our vector is general, correct?
Exactly. Exactly. If I wrote, say, 2, 7, 4, and multiply by 1, that would be proof by example, which is never okay. But all vectors in Rn look like what x1 through xn. Right? That's what Rn means. Does that make sense?
Yes.
Yeah. There is no such thing as proof by example. Okay? Because if it's by example, it's not a proof. There is proof by counterexample, but not proof by example. Any questions at all on Rn being a vector space? Are you all convinced that any of the other 9 of these can be done just without that much problems? If you're not, let me know which one you want to see and I can do it. But I'd rather not do all 10 because we don't have time. Everyone okay with all the rest of the properties? You can imagine how to do it. It's tedious. Okay, so that's Rn, and that's important. So what I'm going to do is I'm going to go through the kind of the most important ones. The next one is M by n. So M by n matrices. All right. So I'm going to do the same thing. Pick a number from 1 to 9. I don't want to do the same one because we already got to experience that one. Pick a number from 1 to 9, and I'll prove that part for M n by n.
One.
1 it is. Okay. Okay. So 1 is we want to show if we have 2 matrices and you add them, you get a matrix. Is that clear? So let me copy this. Good. You picked one of the easiest ones. So our goal is that if we have 2 matrices, and we add them up, we get a matrix. So in this case, let me rewrite this guy. I don't like to use V for a matrix. I like to use A. And I like to use B for a matrix instead of W. And that we want to show that if that this is an element of m by n. Okay, also very easy. So what do I have to do?
Make sure A and B can be added first of all.
Mm-hmm. Right, but we have a definition of addition of matrices. Okay, so we know that from the first week of class, right? We already learned how to add matrices, didn't we?
Yeah, you add each component.
Right, so let's do that. Okay, there's not much to do here. That's a promise. Just takes a while to type it. But what we're going to do is we're going to take a matrix. And by the way, it's important that these are all m by n matrices. So what I'm going to do is I'm going to put in an m by n matrix. And this is one of those, I don't know if they have the ability. Yeah, I guess I can. Let's do it this way. I'm going to make it not look square because that'll like make you think that these are square. So there's going to be A 1 1 dot 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 and A 1 n. And then we're going to have some dot dot dots here. Let's see if I can do it. Basic math, maybe? Yes. There it is. Some more dot dot dots. Some more dot dot dots. More dot dot dots. Might as well make that real dot 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 then. There we go. And this will be a M1. And these are dot dot dots. And a MN. The hardest part about the whole thing is to write this out. And then plus exactly the same thing with B's instead of A's, right? Because we're adding it to the matrix B. Almost there. Now, by definition, what is this matrix equal to?
A11 plus B11, and then so
Mhm.
on and so forth.
Yep. And then A1N plus B1N. And then AM1 plus B1M, M1. And then AMN plus BMN. Is that an M by N matrix?
Yes.
Yes. So we're done. Let me write down, let's make it look pretty. There we go. That's better. And that's the proof. Any questions at all on the proof? Do you agree there's very little to do here? The typing in a computer is hard, but the math is not hard. Any questions on this? Okay, let's do the next one. And that's Pn. Pn, by definition, is the set of polynomials of degree n or less. Okay, not just degree n. You got to have less. Why do we have to have degree n or less? Why
'Cause
can't we just say all polynomials of degree n?
Because not the whole polynomial will have degree less than n within it.
I'm not sure what within it means. It's just a polynomial. So the hint is, let's go over here and see what fails if we don't say or less. Tell me which number fails. And the answer is a bunch of these fail. Or at least a few of them.
If it was Vn plus negative Vm, it wouldn't work. It would not equal 0. It'd have to be n or less.
There's no problem with that, because if you have, say, x cubed minus 3x plus 5, well, negative x cubed plus 3x minus 5, that's still of degree of the same of degree 3 or less, of degree 3. So that's not the problem, actually. 5 is fine. Number 1 is a problem. Why is number 1 a problem? What's x squared plus x as the first polynomial and negative x squared minus x as the second? If you add them up, you get negative 2x, and you're not degree 2 anymore. So if you add polynomials, you can lose degree. Does that make sense? The other issue is number 4. What's the degree of the 0 polynomial?
Whatever you want.
No, no, no. It's not whatever you want. It's a very special degree. What's the degree of the 0 polynomial? Hint is it's very easy.
0.
It's 0. So if you say you only let polynomials in of the degree, say 5 or exactly 5, then 0 doesn't exist. Do you see that? Because 0 is not of degree 5. So that's why you have to do or less. Any questions on that? So number 1 and number 4 don't work. The others are actually all fine. Okay, except no, actually number 1, a multiplicative doesn't work either, because if a is 0, you lose your degree. So there's 3 of them that don't work. Okay, but if we define Pn to be the collection of polynomials of degree n or less, then this is a vector space. Any questions on that? Any questions? Okay, I don't have time to go and do this one. I want to just mention in my negative 2 minutes I have left, just to note some really other important ones are things like the set of all polynomials. So if you take that polynomial and subtract twice the derivative of the polynomial, you get 0. That's actually a vector space. Those are really important. So solutions to what's called linear differential equations are vector spaces. And we're going to be using that. You'll be using that a lot next quarter. But we are out of time. So as always, I'm going to stop the recording.